Okay. Well, it's good to finally see you guys in person. I guess it's been 2 weeks now since I took over the class. Hopefully the transition hasn't been too rough. I finished writing the exam for tomorrow this morning. It's only 23 questions. And I just took questions from for the most part, I took questions from the lecture quizzes that you guys have had. And I modified those. There are a few other questions that I've thrown in there, like do like the electron configuration for an element. There's 2 of those. And then for those same ones, do the electron orbital diagrams. So that's all right, so if we're going to do just for something like simple lithium, right, so you'd have the 1s with 2 electrons, and then you'd have 2s with a single electron. So that would be the orbital diagram for lithium. So that was chapter 5, I believe. So there's a couple of those where you're actually going to have to write it out. You don't need a scantron. It's just going to be for the multiple choice ones, circle it. There's a couple, I think there's like 1 reaction that you need to balance. And then there's like 1 like true stoichiometry problem. So probably your best bet, study those quizzes when it comes to the lecture or the exam for tomorrow. Yeah. And that's an in-person exam, so be there to take it in person. So picking up, I know for those of you who didn't watch on Zoom yesterday, I didn't upload the video yesterday. I did upload it today. And then I'll upload this as part 3, even though it's like 4 slides. So this is just the last little bit of the lecture. We finished off talking about this. We were mostly talking about, for those who weren't there, gas, liquids, solids, and how intermolecular forces determine what state a given compound is going to be at room temperature. So stronger intermolecular forces means that those molecules stick together better. So it's going to take more energy or more heat to break them apart. So you need higher temperatures for those to be liquids or gases versus solids. Get a little bit into heating curves. So this curve represents the amount of heat added in joules versus the temperature in degrees C. And so what happens is, when you have this water as a solid or ice, you can decrease that temperature. So if we were going back down this way, you can keep decreasing that temperature colder and colder and colder until you get to absolute 0 in theory. But when you heat that up, as soon as you get to the melting point, you can't heat up in terms of temperature anymore, because all of the energy that you're putting into your ice is going into breaking the bonds between the solid ice crystals. So those have to separate first. That takes energy. And this is why if you put ice cubes in your water or your soda, it will stay at 0 degrees C until your ice is gone. And as soon as your ice is gone, it'll warm up really fast, especially if it's summer. Then our heating curve takes off again. So we're no longer breaking bonds. And we can heat up until we reach the point of vaporization or boiling. And again, when we get to the point of vaporization, can anybody take a guess why this flattens out?
All the energy is going into breaking apart into gas.
Yeah. All the energy that you put into it gets dumped into separating those molecules into gas molecules. So there are still bonds between liquid water molecules. They're weaker than those in solid water or ice. But they still require energy to break. It actually takes more energy to vaporize than it does to melt. So this is why if you boil water, it's never going to get over 212 degrees Fahrenheit or 100 degrees Celsius until that's gone. And this is why you get really, really bad burns from steam, because steam doesn't have a hard limit on how hot it can get. Basically, you can heat it up until the water molecules themselves fall apart, and it ionizes, and it becomes plasma. But we don't really talk about plasma. So in terms of like what you're expected to know on exam question for this, for like the next exam. Just know that like the temperature at melting and the temperature at vaporizing is going to be constant until you run out of ice or until you run out of liquid water. And then the temperature can heat up again. We do put actual quantities to these as well. So the heat of fusion is the amount of energy that it takes to convert exactly 1 gram of solid or liquid at melting, or sorry, solid to liquid at the melting point. So for example, 334 joules of heat is required to melt exactly 1 gram of ice at its melting point, 0 degrees C. So if you had 1 gram of ice, that's how much heat it would take. If you had 10 grams of ice, it would take 10 times as much energy. So that amount of energy required is dependent on the amount of ice that you have. Makes sense, right? More ice, more bonds to break. The heat of fusion is that reverse process, or sorry, the heat of fusion, well, it goes both ways. So you have to put this energy in to heat it up, to go from solid to liquid. You have to take that much energy out to go the other way as well. So if we want to form those bonds again, you have to be removing energy so that they're able to form. So reverse process, right, is exothermic. So that heat is actually coming out. This is one of the weird properties of, actually, does everything do this? Water has some weird properties. Do you guys remember the term endothermic? Basically means you have to put heat into it. So it's sucking up heat as it's actually sucking up heat as it's melting, because that energy is going into breaking those bonds, and it releases heat as it's freezing. And this makes sense when you put water into your freezer. That freezer is constantly working to remove heat from the freezer chamber, and that heat is coming from, that extra heat is coming from the process of the water freezing itself. So that process is exothermic. Evaporation is now, so moving from our heat curve from freezing, melting, up to boiling or condensing. We're taking those water molecules and giving them sufficient energy to escape from the liquid surface and enter the gas phase. So we'll get locked again into a constant temperature at the boiling point. Yep, like I said, they have enough energy to overcome and become gas. Water, liquid R plus heat, ONS. These are Mr. Guerrero's slides. I'm not sure what he means by this. Interesting. Anyways, so condensation is just the reverse of vaporization. It's a reversible process, so it's also a physical change. But your gas vapor is converted back into liquid. And so just like when we look at evaporation or boiling versus condensation, one of those is endothermic, and it's the one where we're adding heat to create gas. So if we're boiling, to go from the liquid phase to the gas phase, that takes extra energy, and that's why it's an endothermic process. Whereas condensation is actually an exothermic process. So one of the really tangible things that we know about evaporation, or the tangible experiences we have with evaporation, is sweat, right? When you're sweating and it's dry outside at least, like it is around here, that sweat is evaporating. And as that sweat evaporates, it takes that extra heat with it and cools you down. So if your sweat can't evaporate, there's something called the wet bulb temperature. It's basically you take a thermometer, coat it in fabric, and get that fabric wet. The temperature that that wet fabric is, or if the temperature of that bulb in the wet fabric gets above body temperature, humans can't survive in that environment, because our body temperature is regulated by evaporation of sweat. So we won't be able to eliminate enough heat to maintain a stable body temperature. This also affects just like the environment in general. So if there's enough humidity in the air and it's cooling down at night, all of a sudden all this water starts condensing on different things. As that water condenses, that process is exothermic. So in areas with high humidity, it doesn't cool down as much at night because all the water in the air starts condensing and releasing heat that keeps the temperature high. Then the opposite happens in the morning, because as it starts to heat up in the morning, all of that dew starts to evaporate and it cools things down more rapidly than it would otherwise. Which is why around here in the summer it gets really cold at night, and then it gets really hot during the day because we don't have this water vapor buffer that's evaporating or condensing. All right. So let's do this calculation real quick, and then we'll get into the lab. Calculate the total heat in joules needed to convert 15 grams of liquid ethanol, which you can abbreviate as ETOH, at 25 degrees C to gas at its boiling point of 78 degrees C. So we're going from 25, let me write this down, our mass, our T final, T initial. So we're going to start at 25 degrees C to 78 degrees C. Our specific heat is 2.46 joules per gram degree Celsius. And then our heat of vaporization, I see, so we're just heating it up to a gas at 78 degrees C. So the heat of vaporization, so this is delta H vaporization, 841 joules per gram. So this is a two-step problem. The first step, you're going to be using Q equals MC delta T. You guys covered that one? Yeah. So we just take our, oh, sorry, I did these backwards. Our initial temperature and our final temperature. So we can just plug these in, 15 grams times 2.46 joules per gram degree C times 78 minus 25. I have the calculator on here. So I'm going to do this 78 minus 25 is that times 2.46 times 15. So our Q is going to be 1,955.7 joules. But we want to go all the way to a gas. So we know that once we get up to this temperature, we got to add more energy to break those bonds and finally get to the gas phase. So that equation's even simpler. We take, so our Q of vaporization is going to equal our delta H of vaporization, 841. That's joules per gram. And we're going to multiply that by our 15 grams. So then when we do that multiplication, grams cancels, and we're left with joules. So it's going to be 15 times 841. So our Q vaporization is equal to 12,615 joules. So it takes a lot more energy to go from the liquid to the gas phase than it did to even heat from 25 degrees C, which is about room temperature, up to 78 degrees C, which is 3/4 of the way to boiling for water. And then your final amount of energy that it's going to take to go from 25 all the way up to a gas is just going to be the sum of these two. So we'll take our 12,615 plus 841. So our Q total for this is going to be 456 joules. Okay. Now we get to the fun stuff.